So let's talk about something truly fundamental to our modern world, the electric motor. These things are everywhere, absolute workhorses hiding in plain sight. Think about your day, that whirring sound from your blender making a smoothie, that's a motor. The silent hum of your electric car pulling away from a stoplight, a very sophisticated motor. They are the unsung heroes in our vacuum cleaners, our power drills, and even the tiny components that make our phones vibrate. They are, in the simplest terms, devices that convert electrical energy into mechanical motion. It's a beautifully simple principle, a dance between magnets and electricity that we've harnessed to build the world around us. The core idea has been around for a long time, but we are constantly pushing the boundaries of what these devices can do. We always want more. We want them to be smaller, lighter, more powerful, and crucially more efficient. Every bit of energy wasted as heat is a bit of energy not used to move your car forward or mix your batter. In the world of electric vehicles, this is a huge deal. Better efficiency means a longer range from the same battery, which is the holy grail for a lot of engineers and, let's be honest, for all of us who drive them. So, the quest to build a better motor is relentless. Now, building things is my jam, and for years, the way we've built motors has been pretty traditional. We stamp out metal parts, we meticulously wind copper wires around a core, and we assemble it all piece by piece. It's a proven process, but it has its limits. The designs we can create are restricted by the manufacturing methods themselves. You can only bend a wire so tightly or shape a metal component in certain ways. This is where my favorite kind of thinking comes in. What if we could build them differently? What if we could break free from those old constraints and design a motor from the ground up, optimized in ways we couldn't before? This is where the magic of 3D printing or additive manufacturing enters the story. Early pioneers like the brilliant minds at Leap 71 saw this potential. They imagined building motors layer by layer, creating complex internal structures that were simply impossible with traditional methods. Their initial attempts were, well, a learning experience. The technology wasn't quite there yet. The materials weren't right, and the precision needed for the intricate electrical components of a motor was just out of reach. It was a classic case of an incredible idea being just a little ahead of its time. But that's how science works. You try, you fail, you learn, and you try again, better. The biggest roadblock in those early days was printing the most important part of the motor's electrical system, the copper coils. Copper is fantastic at conducting electricity, but it's a real pain to 3D print. It reflects the laser light used in many printers and dissipates heat so well that it's hard to melt it precisely into a solid shape layer by layer. For a long time, printing a functional, dense copper component with the right electrical properties was more of a lab curiosity than a practical manufacturing process. This limitation meant that even if you could print the motor's housing or rotor, you still had to insert conventionally made coils, defeating much of the purpose. But technology never stands still. Fast forward to today and the game has completely changed. We've seen incredible advancements in additive manufacturing. Modern laser-based systems, specifically techniques like selective laser melting or SLM, have been refined to handle tricky materials like copper. Engineers have figured out how to use more powerful lasers, different wavelengths of light, and clever software to control the melting process with insane precision. We can now print fully dense, highly conductive copper parts. This isn't a science fiction dream anymore. It's a reality happening in workshops and labs right now. This breakthrough is the key that unlocks the door to truly 3D printed motors. Being able to print copper coils directly means we can rethink their design entirely. We're no longer limited to just winding a round wire. We can create coils with complex cross-sections like squares or rectangles that pack together more tightly. This is called increasing the slot fill factor, which is a fancy way of saying we can cram more copper into the same amount of space. More copper means a stronger magnetic field, which translates directly into more power and torque from the motor. It's a simple equation, but one we couldn't fully exploit until now. This new design freedom has another huge benefit: cooling. One of the biggest enemies of a motor is heat. As electricity flows through the coils, they get hot, and too much heat reduces efficiency and can even damage the motor. With 3D printing, we can design and build cooling channels directly into the copper windings themselves. Imagine tiny, intricate passages running through the coils, allowing a liquid coolant to flow right where the heat is being generated. This is a level of thermal management that is simply impossible with traditional wire-wound coils. Better cooling means we can run the motor harder, get more power out of it, and make it last longer. To really get why this is so cool, we have to talk a little about how motors are wound. There are two main styles: concentrated windings and distributed windings. Think of concentrated windings as short, chunky coils wrapped around a single tooth of the stator, the stationary part of the motor. This setup is simpler to make and can produce a lot of torque at low speeds. However, it's not the most efficient, especially as the motor spins faster. It creates a magnetic field that isn't perfectly smooth, leading to energy losses and more noise. It's powerful, but it's a bit of a brute force method. Distributed windings, on the other hand, are more elegant. Here the coils are longer and are spread out or distributed across several slots in the stator. This creates a much smoother, more sinusoidal magnetic field. The result is a motor that runs more efficiently, especially at high speeds with less vibration and noise. This is the kind of performance you want in a high-end electric car, where efficiency equals range, and a quiet ride is a sign of quality. The trade-off is that they are more complex to manufacture with traditional methods, involving a lot of intricate weaving of wires. This is where 3D printing can really shine, making complex distributed winding patterns easier to produce. Now let's add another layer: phases. You've probably heard of single-phase and three-phase power. Most of the simple motors in your house, like in a fan, are single-phase. They are cheap and reliable but aren't very powerful and need extra components to get started. For anything serious, like an industrial machine or an electric car, we use three-phase motors. These are powered by three separate alternating currents, each slightly out of sync with the others. This setup naturally creates a rotating magnetic field, making the motor self-starting, much smoother, more powerful, and more efficient. For an EV, three-phase is the only way to go. This brings us to one of the most exciting developments in motor design: hairpin windings. Forget round wires. Imagine using solid rectangular copper bars that are bent into a U shape like a hairpin. These hairpins are then inserted into the stator slots and welded together at the ends to form the coils. Because they are rectangular, they pack together with almost no wasted space, dramatically increasing that slot fill factor we talked about. This can make a motor significantly smaller and more power dense. The challenge, however, is that making and inserting these hairpins is a complex, multi-step process that requires incredible precision. The challenges with hairpin windings are where 3D printing can step in and be a total game changer. Instead of manufacturing dozens of individual hairpins and then painstakingly welding them together, what if we could just print the entire complex winding assembly as a single unified piece? This eliminates the need for welding, which can be a point of failure, and allows for even more complex and optimized geometries than traditional hairpins. We could design shapes that not only maximize the copper fill, but also actively manage the electrical current to combat pesky problems like the skin effect. That's a phenomenon where at high frequencies, electricity tends to flow only on the outer surface, or skin, of a conductor, wasting the copper in the middle. By 3D printing the windings, we can create hollow structures or intricate internal lattices that guide the current more effectively, ensuring the entire conductor is used efficiently. This level of granular control over the internal geometry of a conductor is the kind of thing engineers used to dream about. It's about building the absolute perfect shape for the job, not just the shape that's easiest to manufacture with old tools. This is how we push past the current plateaus of motor performance and take the next big leap in efficiency and power density. It's a fundamental shift in how we approach the problem. And this isn't just theory. Real companies are already making incredible progress. Firms like Additive Drives and Infinity Turbines are at the forefront, using additive manufacturing to build next-generation motor components. They are not only perfecting the process of printing pure copper but are also experimenting with incredible new materials. Imagine coils made from a copper-graphene composite. Graphene is a wonder material, incredibly strong and an even better conductor of electricity and heat than copper. By integrating it into the printed structure, we could create coils that are lighter, stronger, and can handle more current with less heat buildup. This opens up a whole new frontier for performance. So where does this leave us? Today, on July 13, 2025, fully 3D printed motors are still an emerging technology. They are not yet rolling off the production line for every electric car. There are still challenges to overcome in terms of speed, cost, and scaling up production, but the proof of concept is there. The science is sound, and the potential is undeniable. The ability to design and print highly complex, thermally managed, and electrically optimized coils represents a revolution in motor technology. The future for electric cars, drones, robotics, and countless other machines looks incredibly exciting, and it's being built layer by layer. I, for one, can't wait to see what we build next.